The pressure curve broke before anyone noticed the atmosphere was changing. A faint star slipped behind Pluto's edge, and the light did not disappear cleanly. It dimmed in steps, uneven, like something was still holding on to it. That flicker was recorded in occultation data by observers treating Pluto as a stable seasonal system. But the curve on their screens did something that should not happen. It rose, peaked, then started falling while Pluto was still moving farther from the Sun. That reversal carried a consequence no model was supposed to allow. Atmospheric pressure on Pluto was not supposed to collapse during recession. It was supposed to expand slowly, like a delayed breath from a frozen world warming at the edge of sunlight. Instead, the numbers turned back on themselves. And the visual anchor kept returning. The faint stellar occultation light curve tracing Pluto's atmospheric edge during repeated star pass-bys. Each pass showed the same behavior. A soft dimming of the star. Then a sharper boundary than expected. Then a thinning that arrived too early. Like the air itself was being removed from the equation instead of gradually fading. NASA-linked observation teams did not treat it as a single anomaly. They treated it as a broken expectation. Because the same instruments, the same occultation method, had once shown Pluto slowly building atmospheric density across decades. That trend had been stable enough to trust. Now that trust was collapsing in real time. The click promise formed inside the data itself. A single occultation observation forced astronomers to abandon decades of rising atmosphere models when the pressure curve suddenly reversed into collapse. At first, the assumption held: seasonal forcing, nitrogen ice sublimation, a delayed thermal response, Pluto warming slightly as it moved through its orbital arc, releasing gas into a thin but persistent atmosphere. The models were clean, predictive, stable. But then, the next star pass arrived, and the visual anchor returned again. The faint stellar occultation light curve tracing Pluto's atmospheric edge during repeated star pass-bys. Only this time, the dimming did not match the previous curve. The atmosphere was no longer behaving like a continuous layer. It behaved like a threshold system, a boundary that existed only under specific orbital conditions. The prediction failure began quietly. A few data points drifting below expected pressure, then more. Then an entire segment of the curve flattening earlier than any seasonal model allowed. It looked like loss of atmospheric mass, but without escape. No outward flow, no dispersal, just disappearance. And that is where the first reinterpretation hit. The system was not losing atmosphere into space. It was losing atmosphere into itself. The anchor reappeared during a new observation cycle, the faint stellar occultation light curve, tracing Pluto's atmospheric edge during repeated star pass-bys. Now the dimming was shorter, sharper. The transition from star visibility to occultation was becoming abrupt, like the atmosphere had stopped acting as a gradient and started acting as a switch. That shift forced a working explanation. Pluto's atmosphere was not stable air. It was surface-dependent gas. Nitrogen that existed only when surface conditions allowed it to remain in vapor form. For a brief period, the model stabilized again. Everything aligned. Seasonal sublimation matched partial atmospheric presence. Pressure curves made sense if the atmosphere was not continuous, but cycling between states. It looked resolved. until the midpoint of the dataset broke the scale. Long-term occultation campaigns began showing something larger than seasonal variation. The atmospheric peak did not just plateau, it turned. The pressure curve that had once been rising started collapsing in a way that aligned not with time, but with distance from the sun crossing a specific threshold. This was no longer a seasonal atmosphere. It was a conditional atmosphere. The visual anchor returned with new meaning. The faint stellar occultation light curve tracing Pluto's atmospheric edge during repeated star pass-bys. Now, each pass revealed less dimming, not gradually, but in discrete steps, like layers of gas were being switched off. At this point, prediction failure became structural. Every model assumed continuity. Every equation assumed gradual change. But Pluto was behaving like a system with a phase boundary tied to orbital position itself. And that changed what the collapse meant. It was not a slow loss of atmosphere. It was a transition into frost. Nitrogen gas, instead of escaping or persisting, was condensing directly onto the surface as Pluto moved farther from the sun. The atmosphere was not thinning into space, it was falling back into solid form. The anchor appeared again, now with sharper contrast. The faint stellar occultation light curve tracing Pluto's atmospheric edge during repeated star pass-bys. The star no longer dimmed with a smooth curve. It snapped from visible to obscured and back with increasing abruptness as the atmospheric layer weakened. Each cycle revealed less tolerance in the system, less margin between gas and ice, less time for atmosphere to exist at all. And the prediction models began to fail in a new way. Not by being wrong about temperature, not by being wrong about composition, but by assuming the atmosphere was allowed to remain an atmosphere. The data showed it was not. As Pluto continued outward in its orbit, the collapse accelerated. The pressure curve did not just decline, it fractured into segments defined by orbital position. Each segment marked a zone where nitrogen could no longer remain airborne. Each transition marked a collapse event. The visual anchor reappeared again, now almost unrecognizable in its implication. The faint stellar occultation light curve tracing Pluto's atmospheric edge during repeated star pass-bys. What had once been a diagnostic tool became a record of disappearance. Each light curve was not measuring atmosphere, it was recording its absence. By the final observational sequence, the system had stopped behaving like a planet with an atmosphere. It behaved like a planet cycling between two states, sky and surface, gas and frost, presence and collapse. No middle state survived. And that is where the consequence locked in. The atmosphere was not a permanent layer waiting to be measured. It was a temporary orbital condition, a phase that existed only when Pluto was close enough to the Sun to sustain it. As it moved away, the entire system inverted. The sky did not thin, it solidified. The final occultation passes confirmed it. The star returned with almost no distortion, no gradual dimming, no lingering haze, just clean disappearance behind a sharply defined edge. The visual anchor appeared one last time. The faint stellar occultation light curve tracing Pluto's atmospheric edge during repeated star pass-bys. This time, the curve barely bent at all, because there was almost nothing left to trace. The prediction failure was complete. Not because the models failed to describe Pluto, but because they assumed Pluto had an atmosphere that stayed in one state long enough to be modeled. It did not. It switched. And that changed everything about what an atmosphere even means at the edge of the solar system. Pluto was never losing air. It was turning it into ground. The sky was never gone. It just froze. Cold does not remove the atmosphere. It takes it back.